Good morning. This is, or good afternoon, I'm not sure. This is Mr. Martin on topic 5.3, lesson 1. These are the aims for this lesson: to distinguish between primary and secondary cell, to understand how they work and the characteristics of a simple cell, how to charge them, and the concept of capacity of a battery measured in ampere hours and to connect it to coulombs. So very simple aims for this short lesson. What you need to have is the slides already in front of you, the slides that I share with you in the OLP for this lesson. So to start the lesson, the first thing you're going to do is you're going to just watch this video about how to use lemons to produce an electric current. So as a way of starting the lesson, just watch the video and then post on the right side of the chat your initial ideas of what a battery is and how it works. That's, I think, the question that I posted there. What is a battery? How does it work? Initial ideas before we start looking at anything else. So I'm going to continue with this lesson, but you can pause the video if you haven't done this yet. So how does a battery work? Okay, a good way of explaining how a battery works, like always in physics, is to use analogies. So if this is a battery, this is the symbol for a battery, the long, I'm going to do it again. The symbol for a battery here, the thick and short side of the battery is the negative pole, and the positive is the long. This is a symbol for a battery. So a battery could be thought as an elevator. So I'm going to write down here, I'm going to draw an elevator of charges. So these two wheels are rotating. Of course, to rotate, these wheels need to have some kind of energy, and that energy is coming from the chemical energy. Chemical energy in the case of the lemon in the electrolyte. And for some reason, this chemical energy is transformed into electric potential energy. That means that positive charges, we're using the convention here, positive charges are rising to the positive pole of the battery. That means that these charges are then free to fall from gravitational potential to kinetic energy. In this case, when charges fall, they can produce what we call a current, right? Motion of charges in time is a current. So conventionally, we use the unit of charge in Coulomb and the unit of current in ampere, as we saw already there. And in the process, these charges could do some kind of work, I don't know, make something spin. So they work, and the circuit needs to be closed, so these charges, they need to go back to the circuit. So there needs to be enough energy for the charges to go around the circuit and return to the elevator, right? So this is more or less how we can understand the big concepts here, the concept of potential difference, which is that energy per unit charge, volt, potential difference is measured in volt, is equal to joules per unit charge per coulomb. That is what we define as potential difference, right? So a battery is a system that is transforming chemical energy into electric potential energy, right? Energy always measured in joules. So this is more or less an analogy to explain how a battery works. I don't think it's really a very good analogy, but It connects with things that we have seen in mechanics, right? What is the problem with the batteries? This is a common misconception. The batteries, we know, for example, a battery for a car, it's a battery that needs 12 volts, right? And I'm not talking of an electric car. A simple combustion car uses a battery of 12 volts. And these batteries are quite expensive. So a question could be, why don't we just buy, 8 AA batteries, which are very cheap, and we connect them in series, right? Like that, to make the equivalent of 12 volts, which is something that is very easy to achieve, and then use cheaper battery for a car. Or another example, a solar panel. A solar panel could produce around 30 volts, right? And at home we have 240 volts that we need, right? So the question is, could we use, 20 12 volts battery, or, 8 times 30, 8 solar panels to produce the 240 volts that we need and power our house? The answer to these questions is a big no. Why? Why no? Because the energy in a battery is not just the potential difference involved, as we have seen before. It's the potential difference multiplied by the charge. And the charge that the battery can have, or the charge that a solar panel can produce, could be very little. So even though we can have the enough voltage, in terms of energy or power, it is insufficient to use AA batteries to start a car. Remember, this is Joule's law. We saw this in topic 5.1, I think, 5.2, circuits, right? So the problem here has to do with the capacity of a battery. We are going to explore this concept later on. But it is important to understand that the energy is not just the voltage. It's both the voltage and the charge. And if the battery is able to store and push very little charge in a circuit, then we cannot have enough energy. That is why solar panels are not replacing the power in our houses totally. Okay. So, distinguish between an electric cell and a battery. This is one cell, and many cells together make a battery, right? So that's one thing to remember. It's a device that generates electricity from electrochemical energy. And then there are two types of cells. Primary cells, which are only used once and then discarded, like these ones here, primary cells. And then secondary cells, which could be this or this, the ones that we use in cars or the ones that we recharge at home, secondary cells. These are rechargeable. Much better in terms of sustainability, right? So we're going to analyze these two types of cells. What is the problem here? If we want to test primary cells that we buy once and then we throw away, we need to understand that depending on how much, so this is a test for a battery. Suppose that we put here a battery, a AA battery, and this is the capacity of the battery. That means 1,600 milliampere hours means that for example, if we do 20 milliamperes, we are expecting the battery to run for 80 hours. This is more or less how we calculate the charge in the battery. We will explain that in a video later. But if we have a standard AA battery and we change the resistance in the circuit, we make a resistance with a variable resistor and we short circuit the battery here through this resistance. We're changing this resistance, right? And we measure the current in milliamps and the voltage in ohms. The resistance in ohms by looking at the voltage and the current. So for different values of resistance, we are obtaining different currents, and we see how the life of the battery changes. So in the case of a battery, I'm going to use the colors here, red. In this case here, suppose that we have, we measure the current of, well, we adjust the resistance for 4 ohms, and we measure the current here. So I'm going to put a voltmeter here to measure the potential difference across the resistance, right? So if we find the resistance of 4 ohms here, and we measure a current of 200, what we are expecting is that from an initial value of 1.5, when there was no use at all in the battery, it suddenly drops very, very fast, maybe in 10 hours, to 0.8 volts. So this is the first curve. When there is a high current, the life of the battery drops dramatically. If the current is more than that, I mean, if the resistance is more than that, second case, we could expect, for example, for 24 ohms, we could expect this to drop following a certain curve. The models are not very mathematical, very complicated model. There is a curve of how the potential difference drops in time for the second case. Second case. And in the third case, which is a blue curve here, we're using a higher resistance. That means a smaller current. The life of the battery increases. This is primary batteries. We want them to last long because we need to throw them away. So maybe they have a shape like this, maybe. That could be an interesting test. It could be an interesting, it could be an interesting IA. The problem with this IA is that we need to wait a long time, 140 hours to see. So it's long experiments, and I don't know. I wouldn't advise you to do that as an IA. But yeah, probably another variable that we can look at is how the temperature affects the life of a battery that is discharging quite fast. I don't know if there is a model for that, but it could be an idea. So that's primary cells. Primary cells have many problems. They die hard, and we need to throw them away. So we have this problem here. We have batteries that need to be thrown away, and these batteries are really pollutant. You know, they end up in landfills. And the problem is that they contain some toxic materials. They're very toxic. They have acids, they have heavy metals. And all these heavy metals and acids can filter the ground and go into the water that we drink, for example. So that's a big problem, you know. It's polluting the soil, it's polluting the water that we drink. Very, very bad for the environment. So it is even worse than plastic. So there was a school where I used to work, where we had, when I went into the school, there were these plastic bottles. Some student had suggested a very interesting project. He said, you know what, we're going to call every single student to bring their batteries from the house, is to not throw them into the trash. So I'm going to recycle bottles, and I'm going to put batteries inside the bottles. So when I went to the school, there were many bottles in the lab, full, very heavy bottles full of batteries, right? And my question is, okay, so great. All these batteries did not go back to the landfills, but what can we do with these batteries? And that was the question, you know, what to do with these batteries? Now we have them all together in one place. And the problem was that we couldn't throw them away because the impact on that specific area was going to be even worse than by just throwing them separately. It was all these concentrated pollutants that we needed to throw, and many of these bottles together. So nobody wanted to take them out of a school. They were piling in the science lab. So we came with a solution. I was building my house. We put batteries and bottles inside these walls, buried inside these walls, acting as bricks. It could be a good idea to create bricks or to use them to fill concrete. I don't know. But it is a problem, one of the problems with the use of primary cells. Right? What are the problems with, or what are the advantages of secondary cells? Secondary cells are cells that we can recharge, right? And there are different types of secondary cells. Most famous is the one we saw in cars that have acids. They're not dry cells, they have liquids. And these are dry cells: nickel, cadmium, metal hydride, and lithium ion. The nickel cadmium had a problem, or has a problem. It's also toxic, so it was banned in Europe since 2004. Cadmium is also toxic. So even though this is probably a better solution than the primary cells, it's still a problem to the environment. So it was replaced by this metal hydride. And the lithium ion has a very high energy density. That means the energy per unit mass is very high. It means that with a smaller battery, you can power, for example, phones or computers or iPads. So this is why the lithium-ion batteries became so popular, right? How do we charge them? A charger needs to be connected, the positive pole of the charger to the positive pole of the battery. We want a small current to go through the battery in the opposite direction as it will naturally go. It is like re-establishing the equilibrium in the battery by sending a current, a small current to go in the opposite direction. So this is how we charge them, right? So is this like the solution to all the problems? This is what is analyzed here. What is the future of batteries? What are the advantages of disadvantages? So this is a video for you to watch. Peter Bruce from Oxford analyzing the options of batteries that we have in the near future. If we can solve the problems of a battery, we can solve big problems like the climate change, transportation, and many other problems. Because if we have good batteries, we can use electric cars, right? Electric vehicles to go around. We could just use solar panels that store energy in highly dense batteries, with energy dense batteries, to power our house. So the technology of batteries is very much connected to sustainable solutions for climate change and energy storage. So I'm going to pause here where you get to this video. So there are two assignments to do now after listening to this video, and then you have a few questions to answer. The first assignment is to just watch this video and take notes. This video here, you watch it and take notes, and then you're going to answer some questions. The second assignment, these are short videos, 4 or 5 minutes each, is look at this concept again. What is the battery capacity? What does it mean? How to convert ampere hours or milliampere hours into coulombs. So these questions are going to be also asked when we reconnect after you have done this task. So that is the first lesson. I hope it was okay. You can also watch this lesson again if you need afterwards. And next class we're going to start from where we leave this these two concepts I am going to revisit next class. Okay? So have a nice review of these videos, and we see you in a while.